Thank you again. Last time, I mean, we just covered like some motivation why like string field theory is like very useful. So basically, I mean, one motivation. I mean, so we like considered just one motivation, which was like if you don't take into account the like uh, say the mass correction to string states, quantum mass correction, then you get the divergences when you try to compute the string amplitudes. And if you also don't try to like take into account the correction to space-time equation or say Einstein equation, then also you get the divergences. So we considered like how exactly these divergences appear. So basically they show up as some degeneration of Riemann surfaces when you like compute integrals over the moduli space. So that was some extended motivation. And then so basically the cure was we had to, so what we concluded was we had to have a systematic way to isolate the 1pi and 1pr part of the this string amplitudes. And the standard formulation, which is based on the worldsheet theory, Polchinski level worldsheet theory, so that is not very well equipped to handle these issues. So that was one motivation. Of course, there are other motivations. So that was one motivation to like study string theory. And okay, so this was our like brief outline. We covered this first part. So basically, what we said was, since string theory has a very rich gauge structure, what we need to do is we need to have a formalism where we can quantize a very generic gauge theory. And the standard Faddeev-Popov method is not very useful in this regard. So we need to develop a more general formalism, which is known as this Batalin Vilkovisky or BB formalism. If you want to quantize a system which has like symmetries beyond like say Young-Mills. So that was our. So we covered this first part of this talk. What we can learn from this standard for the Popov quantization. And one, the main main point which I wanted to convey in this part was that if you have, so in general, okay, we have gauge symmetry, we do for the Popov quantization, we gauge fix, and that's it. But then a new symmetry emerges, which is this BRST symmetry, which knows about the original gauge invariance. So what are the consequences of this original this gauge invariance on the this 1pi effective action that we discussed in some detail, and that gave us these identities, these word identities, which are known as Slavno-Taylor in this context, and they take this form. So what we did was we introduced sources for the BRST transformation. So these Ki are the sources for this BRST transformation. Pi I are the expectation value. So one point function of your original fields. Gamma is the 1pi effective action. And the consequence of your gauge symmetry can be like represented in this way. So by introducing these sources for the gauge transformation, we can represent, or we can find the consequences of those symmetry by this equation. So that is what that is where we had stopped.
And if you don't mind, I'll just say, because this is what had confused me here. And so this gamma is almost the usual 1pi effective action, but not quite. The 1pi effective action is Legendre transform of generating functions of J for phi. But since you wanted to say that correlation functions involving phi and BRST transforms of phi, this one end, that vanishes. You need also to introduce a separate source of sources for those things that appear on the right-hand side of the BRST transform. Okay, so now you introduce sources for phi and sources for the transformation. Okay, so it's like two objects. Okay, and then you Legendre transform with respect to the first source. So you get like an effective action for phi, but you keep the sources there for the second. So that's what that does. It's a mixed kind of thing, and then that gives this.
So we have introduced this bracket in terms of which the same equation can be written in this way. So we will like come back to this in more detail. So this was just a motivation. So what we are going to do now is to consider the
Just one more
Yes.
thing. If you could go back to your equation, just to say
this one.
no, the one before that one. And if you look at that, you see, if you take derivative with this of gamma with respect to phi, it's removing a phi and replacing it by what is transformed under the BRST transform. It's like a standard word identity. That field is replaced by its transform.
And at this point, you haven't said what other form of Gantt, right?
No. So that we are going to discuss. So before studying the quantization of like this general gauge system, which are more general than say Lie groups, first we shall discuss what are the these general gauge like systems. What is the structure of this set of general gauge system? So let's start. So suppose our theory has a collection of fields, say phi I. Okay, where this I could be, it's a very generic index, so it could be a space-time index or some internal index, a spinor index, whatever is like our system. So and let's denote the collection of all possible gauge transformation by G bar. Okay? And at this stage, we shall not specify what are the possible like gauge groups. So what is the form of this G bar? And as we shall see, it may be a Lie group or a more general group. So now let's assign a parity to each field. So for epsilon denotes the parity of this field phi I. For graphs, say for spinors, etc., it will be like even, and for scalar field, say it will be. So it will be like, so this is defined only up to a mod 2. So it takes value 0 or 1. And so we have this property. When you interchange, you pick up this factor -1 to the power epsilon. So this is our like field system. And now let's consider a general transformation of the field of this form, delta phi I equal to Ri alpha. So this may depend on the field phi and then some parameter var epsilon alpha. So we are using a compact notation where an index is associated not only with some discrete index, but also with a space-time variable. So for example, if you have a quantity like this, so FAB is say GAC and HCB, so there is a sum over C, so it denotes a matrix product not only in index space, but also in function space. So it's more precisely like given by this form. So we have, so with index A, we have this index A as well as a space-time variable X, and then with C, we have Z, and this is summed over, and then with B, we have this index Y. And there is a sum over C and then integral over Z. So this transformation is more generally like denotes this. So this is, this notation is useful. It's called the D-bit notation or something. So just to like see, so we can represent, for example, our familiar say U1 or the diffeomorphism in this way. So for example, if you have a U1 gauge transformation and if you choose R mu of this form, del x mu delta dx minus y, then this transformation. So the gauge transformation written in this notation would be just R mu times epsilon. But now if you follow this notation, there is an integral over y, and then you can do this integral, and then you get familiar del mu epsilon. And similarly for diffeomorphism, you can choose R mu nu rho appropriately, and this will, if you just follow the notation, it will give you the expected likelihood. So it's just like a convenient way of like discussing the gauge transformation.
So just to say for scalars, what is
sorry?
For scalars,
yeah.
So
for scalar here, we don't have the gauge transformation. It depends on like, suppose your scalar has some symmetry, then you have to find that symmetry and then appropriately.
I'm saying just for general for
Let's say,
Okay.
let's say x goes to x plus b. So
Okay.
it should be vi del I.
Okay. So del mu, so it will be something like del mu epsilon, some phi del mu epsilon or something.
Okay, so these epsilon corresponds to.
And so the gauge parameter.
Yes,
Gauge parameter. So now so since we are claiming that this is the keeps our, so this transformation keeps our theory invariant. So so we demand that this transformation should not change the classical action of the theory. Okay. So if you vary this action, so suppose S naught is your action, so the variation would be delta S0 by delta phi I times delta phi I, and let's denote this del S0 by del phi I by this notation S0 comma I. So comma denotes the derivative. So what we want is, we want this quantity to vanish, S0I, and then for delta phi I, we replace R I alpha epsilon alpha. Since epsilon is arbitrary, this gauge parameter is arbitrary, we must have this identity. So S0I times Ri alpha must vanish. This is known as Noether identity, and this holds. So we have not imposed the equation of motion. So these are so this identity holds option. And these Noether identities are obtained even before we have used the equation of motion. And so that's why these are optional.
This is like the Bianchi identity.
Yes, yes. So I'm just coming. Yes. So these
There could be boundary.
there could be boundary term. I'm not considering boundary term. If you have boundary term, then of course there will be some extra. So these Noether identity basically give differential relations among the Euler-Lagrange equations option. Okay. So I will just give these examples for U1 and so for U1, for example, if you have this Maxwell theory, then this identity basically gives you this value of mu equal to 0, which is like, I mean, we know it's satisfied. And similarly for GR, this is this then mu G mu equal to 0, where G mu is your Einstein tensor.
So these are even more silly than.
Sorry?
So these are not like guaranteed, they're more.
Yeah, they are more basic, yes. But yes.
You said for Maxwell theory, local identity for what symmetry?
No. So this is not the, I mean, okay. So here, I mean, we have this transformation.
For Gates.
For Gates. So Gates transformation always satisfies these Noether identities, and we shall take this to be the definition of our Gates transformation. So basically, what happens is Gates redundancy imply that equations of motion which you write down, they are not all independent. So there must be relation between these equations of motion, and these Noether identity basically represent those equations of motion. I mean those relation between the equations of motion. Okay. But we shall take these Noether identities to be our definition of Gates transformations.
Sorry, so why does the next slide? So why does du equal 0?
Then yeah, so F mu nu is anti-symmetric, and del mu is symmetric. So
why is there a relation between equations of motion?
Oh, because equation of motion will be, suppose you have no sources, then it will be just del mu F mu equal to 0. So it's a sort of like okay, you are taking a linear combination, taking derivative and derivative. Okay, so we want to find the general solution of this Noether identity, because these are our these we represent as our definition of Gates transformation. So we want to find the solution of this, and the most general solution takes this form.
Sorry, and just to make sure I'm understanding, so so if I do a delta A mu, I would get if I do a delta A mu, I get del mu delta A mu, I get delta A mu times del mu F mu times delta A mu. That's the variation. Now we put delta A mu to be del mu of epsilon and integrate by parts. And that's how
So the general solution of this Noether identity take this form. So we have, of course, this particular, I mean, this which we started Ri alpha, some say lambda tilde alpha, when this is some parameter. But now you also have a new term, okay? This S0j, which is proportional to equation of motion, and times Tji, where TJI satisfy this graded anti-symmetry property. Okay, so it's like easy to see. I mean, if you just put this expression S0J TJI here, and then use the property of this S0I. I mean, then so S0I will also have some graded anti-symmetry property. So that if you use, then you can show that it vanishes. Okay. So the most general solution of
And what do you mean by, so for instance, in the case of U1, what do you mean by most general solution of del mu?
yeah. So for U1, I mean, okay, it is not going to be like very. It won't play a role this term.
So,
But yeah.
Like, even before you get into that, I'm trying to understand what question you're asking.
So I'm asking what is the most general solution of this equation?
So in the case del mu, F mu equals 0, what is the answer you want then?
So here, I mean, so the first term will be the standard U1 transformation. Okay. And the second term will be something which is proportional to the equation of.
No, I didn't even understand it. So the equation you wanted was del mu, F
No,
mu.
I thought the solving for most general gauge transformation.
Yes.
Not solving for.
I mean, I'm not solving for F mu.
Just in this case, what are you solving for?
I'm solving for this lambda I. So I mean this so gauge transformations. So for example, we represented So we represented this was Noether identity S0I Ri alpha. Okay. And so this what we are trying to do is
Are you solving the inverse problem, like given the Noether identities, figuring out what the
what is the gauge? Yes, what is the gauge? So basically, I mean, okay, here we want to solve which particular, what are all possible transformation which will satisfy the Noether.
Satisfy the Noether. Just to understand.
Yes.
So you're asking, in the case of del mu, F mu is equal to 0.
Yes.
How would you go back to just what is?
So here, let us see. So you have.
You multiply this by epsilon and integrate by parts. Is that what?
Yeah. So this is what will give you this equation.
So you take that, you multiply by an arbitrary, since that's 0 everywhere, you multiply by epsilon x and integrate. For arbitrary epsilon x is 0. Therefore, we integrate by parts, and therefore you find that, and then you notice that del mu F mu nu was variation of action with respect to A.
Yes.
But it's that step you have to notice somehow.
Yes.
Because otherwise, to make it a variation of the action, you have to say that one term was derivative of action with respect to A. So I'm trying to understand how abstractly.
Yeah. So I mean, so what I'm asking is, it's a very simple question. So we have this identity. I mean, S0I R J alpha equal to 0.
Yes.
And I mean, we want to find. I mean, what is the most general solution?
Solution means what?
What possible gauge transformation will keep your action invariant basically?
Good. So you're saying Ri alpha variation delta phi I is Ri alpha clearly does.
Yes.
Because S0I was variation of
Yes.
action with respect to phi I,
Yes.
but something more also.
Something more.
Now and then I answer the question now.
Yeah. So this term which is proportional to this S0J, which was this proportional to equation of motion, and then some quantity TJI which satisfy this property. So if you just put it here, I mean, it will clearly satisfy, just because I mean it's antisymmetric. I mean it has this gradient. So that's the most general solution.
So S0I, S0, comma J.
Yes.
Contracted.
So they will have they will have
As the opposite.
yes.
I see. I see.
Okay. And so the second term is called the trivial gauge transformation, and it is present if we are working off shell. So of course, if we are on shell, then of course, I mean 0, 0. But as we shall see, I mean it makes this gauge algebra what we call open. So I mean right now it's just a word, but we will define more precisely what is the meaning of this open algebra. Okay.
So if I understood the discussion correctly, what you're saying is that there was already this gauge transformation present in terms of R. Now you found that there's another.
There is another, yes.
Which is this S0J
Yes.
TIK, which also seems to lead
Yes, this leads the action in. So the first term of this is it's called non-trivial gauge transformation, and let's consider this one first in some detail. Okay, and then we will come back to this trivial gauge transformation. I mean, okay, we call it trivial, but it's it's not trivial. I mean,
Like
sorry.
like homogeneous written.
What do you mean?
Liquid.
No, I mean, not really. Okay, we will define more precisely. I mean, okay, we will come back to this.
And just sorry, just about this PI there.
Yeah.
So for instance, I would say, so this grading I didn't understand. If the idea was anti-symmetric and everything was bosonic, that's what you want.
Yes.
But if it's fermionic, then you
Then
it's an
yes.
Okay.
Opposite that.
Yeah. Okay.
So let's suppose the number of independent gauge transformations are m naught. Okay. So first we are considering this term. Yes.
For the second part was a non-linear term.
Say this one.
Yeah.
Yeah, it
So
can be
that-
nonlinear. of
that-
course. Yeah. Yes.
So what is in the case of U1? Sorry, you can,
Which one?
this last second term.
Yeah.
In the case of U1.
For a U1, I think, yeah, so this is something which is proportional to your equation of motion, which is proportional to del mu, F mu, and so on. So, but it will be trivially zero in this.
S0J is this d mu F mu, right?
S0J will be, yeah.
It's just d mu F mu.
Yes, it will be just d mu.
So you get d mu F mu, that's d mu F mu
Yes.
alpha.
Yeah.
And
And
maybe
then,
an epsilon
yeah, and
mu alpha.
that will be this T, I think.
In even case, your epsilon alpha is del alpha epsilon.
Sorry, repeat again.
In E1 get.
Yeah.
So your epsilon alpha is del alpha epsilon.
Yeah, I mean, so let's first consider this first term, okay? Ri alpha, this lambda tilde. I mean, this particular term, which is non-trivial. So suppose the number of independent gauge transformations are m naught. So basically, you have these like R. So R1 alpha, R2 alpha, ... R and 0 alpha. Okay, they are all independent.
So these are for different fields.
Which one?
1 to m naught. These are.
No, yeah. I mean, so it depends on what is your this I index in phi I. So it could be like it's a very generic system. So yes, so it will depend on like all the so not only different field but also for what values of I. For example, suppose if you have a mu, then this will be related to what values mu takes and so.
But alpha represents the field, right?
Alpha represent. So alpha represent. I mean, it is something which contracts with
So
epsilon.
is it the change?
Change.
Alpha, R1 alpha is under the change of the
Change.
first gauge transformation
Yes.
of the field
Of
alpha.
the yes.
So all of these represent the change in the field alpha. That
I mean, so alpha is this index. So this is
oh, gauge
yeah, gauge
transformation. Exactly. So then, sorry,
this upside.
I represents that.
I represent one. This is what he was also saying. Yes, this 1 to m. So if all of these are independent, then we can get rid of this m naught number of fields. Okay. And the total dynamical degrees of freedom will be n minus m naught. So to begin with, suppose you had n number of degrees of freedom in the system, and then there are m naught independent gauge transformation. Then you have this n minus m naught dynamical degrees of. And such theories are called irreducible gauge theory. And Yang-Mills theory is an example of such theory. But we can consider a more general situation in which there exists.
This is for me or way too fast.
Uh,
Sorry, this is slowly second point. This
Yeah.
means we can get rid of m naught. M naught is the number of
Yes, it's the number of degrees of freedom. I mean, it represents the. So okay, so let's yeah. So this is the dimension. I mean, so this I runs from 1 to n, whatever. I mean,
those are the fields.
these are fields. Its component. It's okay.
Yeah.
What is the dynamic?
If you don't mind, I'm just writing here. So
Yeah.
R I alpha.
Yes.
This is fields.
Yes. And it's in
And
the
these are gauge.
gauge transformation. Yes.
And this runs from 1 to n.
Yes.
And this is 1
No, 1 to n.
N. And this is 1 to n.
Yeah, I mean this we have not specified
Okay,
so far,
something,
but it's something. Yes.
Is it the dimension of the gear through like
It will be it will be related to dimension of your gauge group. And so.
But sort of dimension of Lie algebra times infinity, right? Because points and space.
Yeah.
But you have to not.
That is an intuitive.
Yeah, it could be.
So okay, so using this gauge transformation, if all of them are independent, then we can get rid of these many number of.
Wait, this I'm not understanding. So the first index was number of fields.
Yeah, number of I mean number of fields meaning okay. So it's not. I mean okay, it's number of fields in the sense. Suppose you have say two fields, a mu and say let's say g mu mu. So this n will be running from 1 to 4 plus this d times d plus 1.
So number of independent.
Independent degrees.
Independent fields. But why is that the number of, the total line, n minus, why is n minus m not the?
Oh, because I mean, so we have these, we are saying that okay, if there are m naught
And not just the number of gauge
gauge transformation.
So, sorry, I thought that's number of fields, that's what.
No, we are saying this is the independent gauge transformation. So, I mean, of course, when you write, I mean, there may be like Ri, it would be Ri alpha, but may not all of them may be independent.
So the gauge.
Yeah, I mean, so we are just subtracting basically the gauge. I mean,
Yeah, sorry, what's confusing is that something very elementary. I thought the first index represents number of fields and second number of gauge transformations.
it's number of degrees of freedom. I mean,
So then how many things the first index runs over represents how many fields you have, right?
how many? Yeah, I mean, how many fields are? Yeah, I mean, okay.
So then the number of degrees of freedom should be that minus gauge, number of gauge transformations, right?
So yeah, so total number of values which I takes is n.
But I have said I takes m naught.
No, not m naught. So these are I'm calling these are independent gauge transformation, not the like all gauge transformation.
I think it's confusing to use the
Yeah.
same index.
Yeah,
I
probably.
is
I mean,
an index which of course runs over all fields.
all
But I
fields.
think he means here
Like
that
from that you can pick a basis of.
Yeah.
any amount of
there are some
Which
M
are
not
gauge transformations.
Uh-huh.
M
So,
naught
for
gauge.
instance, in the U1 case, there are 4 that's
Right.
D
Right.
but there's only one epsilon.
Yes, exactly.
Or
Yes.
one.
So only one you can get rid
But
of.
M naught is that one.
Yes, m naught is that.
But then isn't it, why is it m naught then the number of different alphas?
It's roughly like that.
Yeah.
So in this case, it will be like alpha. Yeah. So you are
M naught
right.
is
Yes.
the number of alphas.
Yeah. So yes, you are right. So in this case, it will be like that alpha will be correlated with m naught if all are independent.
All are
But since I mean I'm going to consider more general situation, I'm keeping m naught general.
Maybe it would help if you flash the expression for E1 again, like you wrote it down.
Yes. This one. Yeah. So here epsilon just takes one value. For example, I mean epsilon has no like alpha index. So in that case, for example, this R mu is associated with A mu index, and there was no alpha was taking I mean just one value.
So you think I is 1 and alpha
So-
is mu or they were?
So here I will be 4
It's 4 and
and alpha is
And M naught is also 1.
m naught
M naught is
also yes. So in this case, I mean
Okay, I didn't understand what you just wrote on that first line, but I understand m naught is the number of independent.
yes.
Okay.
So these are the example of this irreducible gauge theory. But we can consider a more general situation in which I mean not Ri alpha are independent. Okay. So there exists say M1 relation between. And so this means that the gauge transformation Ri alpha themselves have a gauge transformation. And such theories we will call reducible theories. Okay.
Null states for null states.
Yeah. I mean, so in such a case, the original number of gauge transformations will be reduced. So instead of m naught, it will be m naught minus m1, and the dynamical degrees of freedom will be n minus m naught plus n.
There's some relations between the gauge
Gauge
transformations.
transformation. Yes. So let's suppose the gauge transformation of Ri alpha is Ri, and let's put this subscript 1 alpha 1. Okay. So if you change this Ri alpha by this amount Ri1 alpha 1 times some epsilon tilde alpha 1, then also your theory is invariant. Okay. So if all the Ri1 alpha 1 are independent and there are no further gauge invariances, we say the theory first stage reducible. Okay. Yeah.
What would an example of this be where you have, let's say, spin 3 gauge transformations, and then those who transform to the same algorithm, so you have to.
Spin 3. So okay, so I will give So basically, if you have 3 form field, then there will be an example. So it will have
It's not cut down by it became a.
So in the case of this form field, we will see explicitly how it is cut down.
Right. So it's the residual distance, right?
Not residual. So this was the if you have if your this gauge invariances stop at this first stage, then okay, we have first stage reducible theory. But in general, this chain of gauge invariances can continue. And suppose the theory becomes irreducible at stage L, we say that it is Lth stage reducible theory. Okay. So an example of this reducible theory is provided by form fields. So suppose you have a P form field CP. So it will have gauge invariance of this form. So if you change this CP by this amount, D of some lambda P minus 1, where lambda P minus 1 is some P minus 1 form. And so this keeps theory invariant. But now if you change this P minus 1 form by a P minus 2 form in this way, then also it is invariant. Okay. So the theory is still invariant.
You're saying in that case that invariance was triviality.
In which case?
In
Here.
the case that lambda itself is D of something,
Yeah, exactly.
then that
I mean, it will
it was invariant, but was invariant under zero.
Right.
So it was not really an rotation.
Exactly. So this chain can continue. Okay. So lambda P minus 2 can have also this invariance, D of lambda P minus 2.
So if you wanted to count, you would count the number of P minus 1 forms,
Yes.
minus the number of P
Yes.
minus 2 forms,
Yes.
plus the number of
Yes,
P minus 3
exactly.
forms.
Yeah, yeah. So the closed thing, yeah. So in fact, this closed string theory is an example in which this chain never stops, and theory becomes irreducible only at infinity state. Okay. So we say that it has this L infinity structure. But okay, we will come to this later.
So is what I said not an example of this?
Spin 3. So it depends. Okay, so one has to analyze this.
Can you explain it?
So yeah.
I meant to say if you have, so let's say you're doing some sort of spin 3 gauge transformation.
Yes.
By spin 3 means 3 symmetric.
Okay.
And I could do diffeomorphisms on this gauge parameter. And
So that's the original, like the.
Yeah, so it's simple diffeom. I see. You say diffeomorphisms and spin 3 invariances
But
will not be dependent.
yeah, because I do a
Diffeomorphism.
diffeomorphism on the spin 3 gauge parameter, and then
But I think it will be related to the first, like it will still be irreducible, right? Because here you are not. So are you saying, suppose you do a diffeomorphism on spin 3, okay, and then on that transformed field you are again doing some transformation. Is that what you mean?
it's like more like I'm transforming the gauge parameter, and I'm asking, like, I don't know if this is right. So I'm asking if the modified gauge parameter is supposed to be something be the same gauge term.
What is the difference with spin 1? Suppose we're Maxwell lines, Einstein Maxwell.
Yeah.
Yeah. So if you in that case, does it work? Like, it will
Yeah. So it looks to me. I mean, it will still be it won't be the gauge transformation for gauge transformation. But okay. I mean, I should maybe check it more.
we can.
Okay, so this was so this is the general structure we can have for this non-trivial gauge transformation. Now let's consider this trivial gauge transformation and analyze them. So the trivial gauge transformation take this form. Okay, so del mu phi I SG, they are proportional to this equation of motion S0 J, and this mu Ji. I'm okay changing the notation. Instead of T, I'm calling this mu. And mu ij takes, I mean, it satisfies this antisymmetric property.
So Mritunjay, this writing it in this plus this minus this plus this. That
You mean here?
no, yeah. Right. So in some sense, it's a matter of convenience, not a principle.
Yeah.
Because if you were clever enough, you could just find out the most
Of
generally
course,
independent case.
Yeah, of course, yes.
Yeah, but it may be more convenient.
Yes, I mean, if you want to work like in a covariant way and so on, then I mean, it becomes very, even I mean, dealing with the irreducible theories like general Yang-Mills theory and so on. I mean, if you are working purely like with independent degrees of freedom, then it becomes very complicated. I mean, so let's consider these trivial gauge transformations. And now let's suppose this delta phi I, delta R phi I, which is denoted by Ri. This is some generic gauge transformation, which can be trivial or non-trivial. And let's work out its commutator between a trivial gauge transformation and a generic gauge transformation.
The trivial means?
Trivial means they are proportional to. Yeah, I mean, yes. Trivial means the proportion. I mean, the one which is proportional. I mean,
mu is T.
Mu is T basically.
Mu is T.
Mu.
Trivial is with the T.
Yeah.
Trivial means proportional to the equation.
Equation of motion. Yeah, trivial means it's proportional to equation. So on shell it went. So let's see what is the commutator between this trivial and some generic.
Everything was proportional.
No, not R. I mean, we had two terms, right? I mean, this is not proportional to equation of. This one is
changes, whether the changes.
change.
Right.
Yes.
So the trivial one is a gauge transformation no matter what the equation.
Sorry?
The trivial one is a gauge symmetry no matter what the equation.
Yes. No. So yeah, it is proportional to equation.
Yeah, and hence it is.
Yeah, so it is independent of what is the solution of the theory.
But even the non-trivial one was a gauge transformation of shell.
Yeah, exactly.
So-
Yes.
Okay, but as you said, this one is that the variation itself is proportional.
Yes.
Equation.
Yes.
It's not that I mean, partly the fact that it's proportional to equation, but also the fact that this mu might.
Yeah, of course. That is what makes it like satisfy this. So okay, so if you work out the commutator of this trivial gauge transformation and some generic gauge transformation, then I mean it's a simple algebra. So okay, maybe okay, the result is it is proportional to the trivial gauge transformation. Okay. If you work out the commutator between this trivial gauge transformation and the generic gauge transformation, then it is proportional to the trivial gauge transformation. Okay. And algebra is very simple. I mean, okay, del R phi I is Ri, but it can depend on phi I, so that's why you get some derivative, and then you have to use you have this trivial gauge transformation, and if you take this derivative, then okay, you use this to replace some terms, and then you can show that in the end it is proportional to this trivial gauge transformation. And utilize some new quantity, but okay, it satisfies this problem.
But mu tilde does satisfy the equations of motion.
Not mu tilde. I mean, mu tilde is just some this quantity. Basically.
No, but earlier that mu was.
Yeah, mu is this point. I mean, mu is just t. Yeah, I mean, mu is just t.
And t was proportional to.
No. T was not proportional. T was just some arbitrary quantity. Which only thing we are demanding is it satisfies that graded. I mean, that anti-symmetry. That's all.
And t or mu depend on.
Yes.
So this trivial gauge transformation exists in like theories which we wouldn't call gauge theory, right? Like,
No, I mean, for example, if you have supergravity theory, then this will exist and so on. In string theory, it exists.
but even in the scalar field.
Yeah, of course. In scalar field theory, Yang-Mills theory, it will not.
No, Yang-Mills is a non-trivial gauge theory. I mean, like any theory, if I just write S0I with anti-symmetric, then it's
Yeah, of course. Yeah.
So probably this trivial will only play a role when there are also.
Yeah.
so when you say irreducible, like that's always there. But
Yeah.
non-trivial gauge
Yes.
parameters also
Right.
exist.
Right.
So can you give an example of trivial gauge transformation?
Trivial gauge. Yeah, I mean, so this is, I mean, so anything, I mean, okay, so you take U1, I mean, have something proportional to equation of motion multiplied with some quantity Tij satisfying this property, so it will be trivial.
But why are you multiplying with Tij?
Because that's, if you don't multiply, then it won't satisfy this equation. There's no iterate. So, yes. So, what we find is, okay, since this commutator of trivial and some generic gauge transformation is proportional to trivial gauge transformation. So, this shows, so in group theory language, basically it means that trivial gauge transformation forms a normal subgroup of all gauge transformation G1. Okay, let's say it is H. Okay? So if you have a normal subgroup, then at like finite level, it means that some G inverse belongs to H, and if you work out its infinitesimal form, this is what you will get. Okay? So if you have such a situation, then we can try to consider a coset. G bar by H and just work with this coset. Okay. In many theories, such as theories with Lie group, we can just work with this coset, and this is the reason we usually don't discuss trivial gauge transformation when we discuss Yang-Mills theory. Okay? But this is only possible if the commutator of two non-trivial gauge transformation does not give a trivial transformation. Okay, and this is not always guaranteed. So, for example, if you have supergravity theories, the commutator of two non-trivial transformation may give a trivial transformation. And then we cannot just work with cosets. We need to consider the full group G bar.
But if you work with the coset, then this commutator within that coset will just be called 0, right?
Not 0. I mean, so then so if you transform by like two non-trivial transformation, it may give you trivial transformation.
But because you're working with coset, you're calling trivial 0.
So
I mean identity, whatever.
No. So I mean, I'm not working with coset. I'm
No,
saying.
I'm saying, suppose you were to work.
Oh, okay.
Okay, then you would replace the right hand side there by just by zero, right? I mean, I'm trying to understand why you cannot work with cosets even in that case.
So because I mean, so coset is useful if like you have this property, right? G inverse belongs to H. When you have so G times H is equal to H times G. I mean, so
But that you just proved, right?
yeah. So in this case, I mean, if you have this situation, okay, I mean the commutator of so this is always true. But what I'm saying is, suppose the commutator of two non-trivial transformation gives you trivial transformation. Then it is not. I mean, then we cannot work with coset.
I'm just trying to understand why that's the case. Because coset is basically saying that any two elements that differ by H are
Yes.
treated as zero,
Right.
right? That if it's just so, why can't we just work with the coset and say that if I get a commutator which is, we do this all the time, right? I mean, if we get two supersymmetries that commute up to a gauge transformation, we just say it commutes.
Uh,
That's the kind of thing I'm asking. So why can't we just work with the coset and every time you get something
yeah, I
that
mean,
is
so but you will be missing out I think interesting physics in this way. So if you are working on shell, then you can always do this.
but
So
something like this. Okay.
yeah. So but if you have off shell, then not.
He's trying to make everything optional.
Yeah.
So
So
even off shell, I mean the coset relation is off shell.
yeah. I mean, so
So I'm just any two elements that are identified by the coset, I'm calling the same element. I could do that off shell.
okay.
This is something basic, I know, but I don't know.
Okay. So yeah, I mean, this is okay. Okay, let's go ahead and
Yeah.
then see if we can come back to this.
In supergravity, non-reducible transformation are different with
Non
the gauge transformation.
non-trivial.
Yeah, non-trivial, they are gauge and they are different.
There are some not. There will be some supersymmetric transformation. Yeah, some super if you. Okay. So of course, this trivial gauge transformation will vanish if we are working on shell. So in such a case, we say that the gauge algebra only closes on shell, and this happens in if you have these supergravity theories. Okay, so
Wait, you went through one slide. Sorry.
So I'm not saying anything new. So trivial gauge transformations vanish if we are working on shell.
Okay.
And we just say that okay, gauge algebra only closes on shell. That's what I repeated. So okay, so this was the these two kinds of with this gauge transformation we had, and now let's see. I mean, what is this? What is the structure of these gauge transformation? Okay, I mean, so far we have just described these two but what is their structure? What kind of functions encode? I mean, information about these gauge algebra. Let's discuss them. Okay, and for now, let's just focus on the irreducible case. So consider two gauge transformation of this type, the non-trivial ones.
Irreducible, non-trivial. Sorry.
No. So irreducible. Okay, so there are two things. Even with
Irreducible is the one which is not like concrete.
yeah.
There are
No.
no
So
constraints.
irreducible.
No constraints of constraints.
Yeah. So no
I-
constraints. Yes.
Okay, so the case where ordinary Fabi property.
Yes. Right. So let's work out the commutator of these two gauge transformation. If you work out this commutator, again, it's a simple algebra. So delta 2 phi I would be proportional to Ri alpha epsilon. This var epsilon 2 alpha. Then when you again, since R can depend on phi, when you take the second variation, then there will be a derivative of this R, and okay, the delta 1 phi will give you R. So in the end, you can show that okay, you have this kind of structure. Okay, Ri alpha with a derivative, and then R with then with
Basically, you vary the variation.
yeah, basically yes. So if you have this commutator of these two gauge transformations, this is what you get. So, but the commutator of two gauge transformation should also keep the action invariant. Okay. So the commutator should also be a gauge transformation. Okay. So we can also write it in this way: delta 1, delta 2 phi I equal to some delta 3 phi. Okay, and since this delta 3 phi I is a gauge transformation, it must also satisfy the Noether identities. Okay, so a general solution of right hand side. So we have so in this first line is what we explicitly worked out, but because this right hand side satisfies the this Noether identity, you can also write it in this way. Okay, one term which is proportional to R, and the second term which is proportional to equation of. And you have more indices because to soak up these indices present in this warrant. So
You have three different symbols for it. You had Tij,
we had no. So this T is different.
and then in EIT.
EEJI. Yeah, because it has now more indices.
Okay. This is that thing with the symmetry.
Yes, yes.
EIJ is this.
Yeah, Tij. I mean, yes. So this Eij is an analog of this Tji, VHDRT. So yeah. So basically, and this T and E, of course, can be written are some tensors, and they encode information about this gauge structure. So in the normal case, in the Yang-Mills case, we call this T gamma alpha beta as the structure constant. But in general, they can depend on field phi. And the second term, which involves this Eij alpha beta, it is present because the commutator of two gauge transformation may be trivial. And this its presence basically means so you have to take care of this if the gauge algebra does not close it. And okay, again, I mean this T and E satisfy some this anti-symmetry property which you can work out from the general. I mean first the original T which we have written down, and the parities of this also you can work out. I mean these are not very important. What I want to show is okay, I will come to the punchline soon. So the open and closed algebra are defined in this way. If this Eij alpha beta is 0, so this the term which is proportional to this equation of motion, if that is 0, we call it closed algebra. But if it is not 0, we call it open algebra. And the gauge algebra corresponds to a Lie algebra if it is closed, and this is structure constant T do not depend on the field phi. These are our standard usual Yang-Mills theories. But the gauge theory, in a generic situation, they allow for this open algebra. And the usual Faddeev-Popov method will be inadequate for quantizing.
Supersymmetry transformations without auxiliary fields are less. Second.
Supersymmetry transformation without auxiliary may not
Not really gauge, but yeah, without the auxiliary fields are brought in too close here.
Right.
So extra piece of play.
So
Wait. So just to get this, as you said, normal Lie algebras, the structure constants are field independent.
yes.
But if they were just field dependent, there's no problem using that.
It will be more involved, but probably you can still use it because
But you say the key point. So there were two things you brought out.
yes.
One is that the set of gauge transformations
We
may
have
be,
gauge transformation for
So,
gauge
gauge
transformation, and then
and second these
open
other
closed,
things.
yeah.
Okay, and which is the key point?
I mean both.
Both of them. So
Both of
if either of them operate, the normal Faddeev-Popov is
I mean, so in the if you don't have this gauge transformation for gauge transformation, then you I don't know if anyone has tried, but what I can see is there will be I think problem.
just say even if we don't have the gauge transformation, but we have these T's, then the normal Faddeev-Popov will have
trouble. I think you will have to modify the
standard
standard
set of gauge transformations.
Yeah. You mean in the Faddeev-Popov?
Yeah.
Yeah, you can
You
include this.
So
Even in this way, like if you have gauge transformation for gauge transformation, of course, if you insist on using like Faddeev-Popov method, what you can do is you introduce a new ghost field and ghost for ghost and try to work in the standard framework. Nobody is stopping us from doing that. But it will just become very ugly.
This is just a systematic.
Yeah, this is what we are going to discuss more systematic way of handling.
What do we use to figure out?
Sorry,
What do we?
I think you have to use this BB, which we will discuss. So another point is for any gauge algebra, one important this constant comes from imposing this Jacobi identity. So this is the Jacobi identity. If you have three say gauge transformation, you take commutator of 2 and then commutator with for the third one, and then do a cyclic sum, then it must vanish. This is the Jacobi identity. And in this context, if you like what we just discussed here, if you work out this commutator, you see that this Jacobi identity gives the relation between this structure constant T and this Eij alpha. Okay. So okay, this A and B are some quantity which can be expressed in terms of this R and T. Okay? So they have some complicated form, but okay. So this Jacobi identity gives us these derivations. This constraint on this R, T, and E. So only those structure functions, this T gamma alpha beta and Eij alpha beta are allowed, which satisfy the constant which are imposed by Jacobi. Okay, and the solution of these constants lead to new structure functions into the theory, and which encode more information about the gauge. So, for example, if you have irreducible theory where you don't have the gauge invariance, for gauge invariant, then the solution of Jacobi identities take this form. So we had so this Jacobi identity was expressed in terms of this A, where A was given in terms of T and E. But for irreducible theory, you can show that if you have an expression like this, it satisfies the Jacobi identity, where there are some structure functions which satisfy like this constraint.
What about B?
Yeah. So B was here. So yeah, I mean it appears in this constant.
So there should be solutions for A and B, right?
A and B.
But
No. So A and B are not like independent quantity. They are just given in terms of P and E. I mean this P and E. Some combination of P and E appears here, which we are calling A and B.
but they are independent things, A and B.
Independent in what sense? So they are given in terms of like this T and E. Yes.
Right.
So they were our original like this structure functions. Okay. And what we are saying here is this whole combination here. If you have a quantity like this, it will satisfy the this Jacobi.
What are you solving for?
Sorry.
What are you solving for?
So we are trying to find what is the like equation satisfied by these structure functions.
Sorry, just one second to understand that. The E was the structure constants of the normal, the non-trivial gauge transform.
The one which is proportional to equation.
So E was that.
Trivial. Yes.
And T was that anti-symmetric form.
No, which
So
no, so this T, okay, so there are two T, okay, I sorry for yeah, I'm very sorry.
Okay, so the normal structure.
Normal
So
structure.
T is FABC.
Yeah.
T is the normal structure.
Yes.
And E is that anti-symmetric.
Anti-symmetric. Yes.
And so the normal structure constants and anti-symmetric thing
Yes.
have to together satisfy
By some identity because of the Jacobi this thing. But if you put in like this Jacobi identity, they give rise to new structure functions. Okay. So you have like this constant. I mean, the D must satisfy like this kind of.
T is now what I'm saying.
So D is just. So you have like this combination, okay, which is given in terms of this A and B. Okay. So when you put in this Jacobi identity.
Not even remember again.
So A and B are, if you have this Jacobi identity. So what you do is you put these transformations, these gauge transformation in the Jacobi identity.
Yes.
And then this is what you get, which is given in terms of this A and B. Okay. Where A and B are some functions of R, T, and E.
Okay, so A is a part of the Jacobi identity that is proportional to the normal bit.
Sorry.
Non-trivial bit. And B is the part of Jacobi identity
Which is proportional to the
trivial. Yeah.
So I mean, a function of this kind will satisfy the Jacobi identity we have. But and where this D, if you put it back in the Jacobi identity, it must satisfy this kind of relation. But a general solution of this identity introduces a new structure function, okay, in the theory, which is this mkji alpha beta. Okay, so it's a, like a yet another like structure functions present in the theory. So the Jacobi identity gives two new structure function dn. Okay, they have some certain property which are not important. So
in the end, our data
Yes.
is the follow.
so what we have
a general solution to the Jacobi identity
yes.
in terms of two things.
So we had this E and this T structure constant, and then we have two new this D and N.
So E and D and D and M, and but then there were some equations. Oh no, these were.
Yeah, they have to satisfy. I mean, these identity, but they are independent. I mean, these D and M and this A and B are given in terms of this other quantity, but this D, M, and this your original E and this T with three indices, they are all independent structure functions of the.
If this process continues.
Okay, yeah, we are coming to that.
See, sorry, I didn't understand. If I knew my Gauge transformations, I also know the structure constants. Right?
I mean, so we have this intuition of the like standard ones where we don't have this trivial Gauge transformations.
No, but structure constants including the trivial part. If I know my Gauge
No, but if you
transformations,
but if you try to solve the Jacobi identity, I mean, you will see that okay, yet I mean the solution will have like they allow for other structure functions.
You're giving me the generalization of this mathematical structure of Lie algebra.
Yes.
So okay, so I understand that if I had normal Jacobi identities, I would get Lie algebras.
Yes.
Okay.
Yes.
Now you're giving me slightly weaker Jacobi identities because I am allowed to have this T part.
Yes.
So you're giving me some other solution.
Yes.
Okay, so Lie algebras were characterized by just structure constants. This other solution is characterized by structure constants
Yes.
and something else.
I know. I mean, so they have this new structure function. I mean, okay, these are like E, D, M, and so on. So this
Which are then constrained by an equation.
they are they are of course
So
they
they're
have to
not fully
satisfy.
independent.
But I mean, there are more. I mean, so there are many like equations, and then there are like
Some system of
some system of like equations.
some system of equations and derivatives.
Yes.
Okay.
Could you explain why we need Jacobi identity?
I mean, they are always satisfied. I mean, Jacobi identity is like if you have any Gauge transformation and just work it out. I mean, it will be zero.
Associated.
Yeah, it's
You can do the finite transformation, A, B, C, and do it in any order. And expand that in infinitesimal reduction. So the fact that A, B, C is well defined is Jacobi.
okay. So one convenient way.
Just to add on that, how do we know that there are no additional constraints to your Gauge theory? Like
No, there can be additional, like if you take the commutator of commutators and so on, I mean, continue this process. So in the standard Yang-Mills case, it will stop. But if you have like more general situations, then I mean, you may get a new higher like structure functions. And so. So
You're saying that if A, B, C is associative, E, B, C, D might not be? Is that what you're saying?
yes, I mean, if you take so there is a very specific like when you consider Jacobi identity, there is a very specific this cyclic sum and so on.
But that just represents the fact that you do three finite Gauge transformations, and no matter which order you do it in, you get the same answer, right?
Yes.
But in the normal situation, once you've got that constraint for three, you don't have to do anything else.
Yes.
Are you saying that changes?
I think if you have a so no, so in this context, no. This three will
likely to change.
yeah. So this three will be like this thing. But okay. So but here you have to like do this cyclic sum. And that is of course you have to take into account. So one convenient way to write down these identity which are satisfied by the structure this tensor. So okay, we have a very complicated set of like these equations. It satisfies some some complicated looking equations. But one convenient way to import all these equations or at least give a simple looking form is by introducing host field. Okay, so if you have a host field, say C alpha, which has opposite statistics to the original, I mean, the gauge parameter epsilon alpha. So suppose you, associated with this gauge parameter epsilon alpha, you introduce a ghost field C alpha, which satisfy this property. Then in terms of these ghosts, you can write down the equation satisfied by the various tensor structures in this way. Okay. So, and this anti-symmetry property of ghost automatically takes care of all the cyclic sum and so on. So we had. It's just a convenient way of like.
So the first one is the commutation of two gauge transformations. The second one is the Jacobi identity.
Yes. A third one was the solution of like this. This D, we had this solution of this A in terms of D, and D when you put it back in the like it should satisfy this Jacobi. So that represents like
How many C's are there? Three, right?
I mean C just one. I mean it's just
in the third line.
yeah, there are three. Yeah. So by commuting more and more gauge transformation, you can in principle obtain new structure from it.
Is any relationship between these ghosts and the Vilkovisky ghosts?
Yeah, there will be. So these new structure tensors would have more and more indices, and they will satisfy some complicated identity. In Yang-Mills theory, these higher order tensors vanish. That's why we never talk about these. So for closed algebra, there are not usually many structure functions. But if you have an open algebra where you are allowing this trivial gauge transformation proportional to equation of motion, then there can in general be many tensor structures and complicated relations between. Okay. So far we have considered only irreducible theory. If you have reducible theory, gauge transformation for gauge transformation, then the analysis again proceeds in the same way. But extra complication is that there will be non-trivial relation between Ri alpha, and they will lead to new structure functions of the theory. So this means that the number of structure functions and the relation between them increases considerably for higher order reducible theories which have open like sort of algebra. So the analysis of gauge structure of such theories in general becomes very complicated, and we need a more systematic way to deal with such theories. What is the strategy we are going to follow? So what we want is, or what we would like to have is a generating functional which should know about the structure functions of the theory, and it should satisfy a simple equation. Okay. So this generating functional should satisfy some simple equation which should produce all the relation between the structure functions.
So can I ask the basic hypothetical? So you have these non-trivial transformations and trivial transformations. If you include both of them, you just end up with the Lie algebra.
No.
Why not?
So Lie algebra is only, I mean, there you don't allow this trivial.
No, but now trivial is part of my gauge transformation. So it's just
yeah, I mean, so Lie
Lie
algebra. So, okay.
gives gauge transformation.
No, so Lie algebra has a very precise definition. I mean, so that definition is like does not include this trivial.
The structure constants are field dependent.
Yeah, of course.
Oh,
that is
field
of course.
dependent.
Yeah. Yes. So what we would like to have is, suppose you have some function s, which is a function of some original variable phi I, and new variable some auxiliary field ki, and suppose this function you expand in power of this auxiliary fields here. Okay. So s of phi I times some k or del s by del kj. So what we want is that the coefficient of these various powers of these auxiliary fields kj, they should be written in terms of these gauge structure functions. It is all E, T, dm, etc. And moreover, and let's suppose the generating functional S satisfies some simple equation such that when we expand this equation in power of these auxiliary fields K, then we produce all the equations involving these gauge structure functions. So if these two things can be done, then the analysis of the arbitrary gauge theory can be done systematically. So, and moreover, the quantization of such theory, we would see that it would also be easy to handle. And this Batalin Vilkovisky formalism, or it's also called field anti-field formalism, is designed to achieve exactly this. So the main lesson we learn from this is what we want is we have in a generic gauge theory to analyze the generic gauge algebra. I mean, it is more involved. And we want a more systematic handle on like this. And this is what we are going to do. Okay, so let's discuss this BV formula. So we will first discuss the classical aspect of this, and then we will discuss the gauge fixing and quantization.
The various different structure constants, I have a very shaky understanding of. Is that not going to be important from now on?
Yeah, I mean, it won't be, I mean.
Now this will be on its own.
Yeah, it will be on its own, but the motivation was that because it is like more involved, so, and the formalism which we are going to discuss, I mean, it will systematically take care of.
Great, so now I can forget.
Okay, you
about
can
that.
So the main motivation was to show you the complications.
Very effective demonstration.
Can you explain what were the downside of using this Kadai-Popov?
Yeah, so Fadipopov, the standard Fadipopov, which we discussed in say Peskin, Schroeder, and so on. So that's designed for like Yang-Mills kind of theory, where you don't have gauge because you introduce ghost once and then you forget about it, and then you are very nice. I mean, you can divide by the gauge volume, which amounts to including these ghosts in the path integral, and that's it. But now suppose you have this, all the gauge transformations are not like independent. Okay. Then I mean, all the procedure which you follow in Fadipopov, there will still be some redundancy. So you still need to take care of that. I mean,
But you can introduce those for,
yeah, you can try,
but it will be complicated.
It will be complicated, and no one has tried.
And I thought you were saying that in string field theory there will be an infinite step
Yes,
process.
yes.
But this formalism will be able to do it one shot.
Yes. So this is what like we are. So what we will do is we won't go through historical development. We will just describe the formula.
In string theory, it will be infinite because you have infinite number of
fields.
strings.
Yes. Infinite number
Well,
of fields.
on the world sheet of the string, we are the ordinary Fadipopov works really good.
Yeah. I mean, okay. First point. I say, yeah.
String field theory.
Yeah, string field theory. So okay. Again, let's suppose our theory has a set of these fields, II, which is described by an action S naught. And let's for now consider the reducible gauge theory. So there are gauge invariances associated with the gauge parameters. Okay. So in particular, this field phi I have this gauge invariance, which is given by what we have just seen, Ri alpha lambda 1 alpha. Okay. So this is the 0th level of like gauge transformation, and then reducible means this lambda alpha 1 will have further gauge invariance. Say let's say this R tilde alpha p lambda p2. So this lambda p2 is first level of like not 0th, first level of gauge invariance, and so on. So now for each level of this gauge transformation, what we do is we introduce ghost fields in a specific manner. So what we do is for this original gauge parameter, say 0th level gauge parameter, we introduce a ghost field C alpha 1 whose statistics is opposite to this gauge parameter. Okay. But for the first level this gauge parameter lambda p2, we introduce a ghost whose statistics is same as lambda p2. So we repeat this procedure, assigning alternate statistics to the ghost variable in this.
Sorry, I thought in the form field action that you write for string theory, the second level thing was actually a first level for some other form field.
First level for sorry, repeat again.
Like this gauge parameter is going to gauge parameter plus B or something.
Yeah.
I thought that gauge transformation was the gauge transformation.
Yeah, exactly. So I mean,
first level, second level.
okay, so the 0 level is your original one. Say lambda. So suppose we have P form field. So lambda P minus 1 was the 0th level, and this lambda P minus 2 would be the first level.
I don't know the big shots mixing kind of thing.
No, just space-time action for like the phi field, the one fields. So I thought the gauge transformation of the gauge parameter was itself like the gauge field for that gauge transformation.
No. So that was the gauge transformation of this your first. I mean 0th level gauge transformation.
So if I don't know what letter A, I suppose, if C goes to C plus B or something, that's a 0 gauge.
C goes to
C3 goes to C3 plus B lambda.
yes.
That's this lambda is now a 0 level
Yes.
gauge transformation.
Yes.
And lambda goes to lambda plus B or something.
Yes. So that is second. I
But I
mean
thought
the first.
that gauge transformation was induced by C.
Yeah, I mean it is induced, but it has. I mean it is present precisely because your 0th level gauge transformation has this redundancy.
What is it? It's a triviality. It's just
Yeah.
a triviality.
Yes, but like he's treating, I was wondering since both are the same.
No, so I'm not saying these are the like gauge transformation of origin. I mean, what we are saying is this lambda alpha one has this new transformation,
Yes.
which keeps your original like
Triviality.
Yeah, I mean, it's a trivial.
Number one is trivial.
But it is the first level gauge transformation.
Yeah, I mean, okay, so it will induce the like it will trivially keep your original system. I mean, invariant.
Okay.
Yeah. So I mean, so it's the same thing what we considered before. I mean, nothing
Yes,
different.
okay, I'll ask you.
Okay. So we have this.
There's the fact that you're overcounting it.
Yeah.
No, I understood that part. Okay, I'll ask you.
So what we do is, okay, we introduce this ghost field for each level of these parameters, okay, assigning alternate statistics to this ghost value. So all the lambda will have same statistics, either bosonic or fermionic. But this assignment means that this ghost field CA, which you introduce at level A, differs from the next level, A plus 1 level ghost field by 1. So you introduce this set of like ghost field in the system. Okay. So we have so let's call all these original field and all these set of ghosts as fields of our theory. Okay. So we have original fields phi I, then we have ghost C alpha 1, then we have ghost for ghost, which is CP2, then we can have ghost for ghost, and so on. So all of these, let's call them fields. And now, let's. Yeah.
What is alpha and the P superscript?
Yeah, so this is associated with your this original like this transformation.
And P
And P is associated with second level, like
okay, and so on.
and so on. So
At this stage, you're dealing with a non-irreducibility.
I'm dealing with more general.
Also that.
Yes, yes, every time. And yeah, right now that does not play any role. So it's like the same. So let's call all of these to be this. Let's denote them by capital phi. Okay. And for each of this capital phi A, which means for ghost as well as for the original space-time field, we introduce this anti-field phi star A. Okay. And how do we introduce? We assign opposite statistics compared to phi A. Okay. So for phi star A set has this phi I star, then C alpha 1 star, CP2 star, and so on. Okay. So this we will call the anti-fields in the system. And these anti-fields, if you now recall back the like our first like last lecture, so these can be thought of as sources for the gauge transformation.
So what is this star?
Star is just a notation.
But is it like a P form will remain a P form only, but Hermitian one? Hermitian?
No, not Hermitian form. It's I mean, it will have some property which we will discuss. But star is just star is not a Hermitian conjugate. Star is just a notation. It has nothing to do with any mathematical operation.
What are you doing to phi I to make it phi I star?
Right now it's just a field. We will see. I mean, what we are doing. Okay. So I mean, yes. Hello.
No, I had a doubt. These capital C alphas ghosts, they were introduced before we tried to fix a particular gauge in the path integral.
So very important point. Yes. So I mean, we have done. I mean, okay, we have introduced these ghosts without doing any gauge fixing. We are just dealing with the classical theory only. Okay. It's just we are introducing in the system these ghost fields.
When we do it in the path integral, more ghosts will come.
So no. So no new ghost will come. All these will take care of path integral. We will see. I mean, okay. So this is the difference from the usual Faddeev-Popov method. So in the usual Faddeev-Popov method, we first gauge fix, then we do the quantization, and in the quantization procedure, we introduce these ghosts. Here we have the classical theory. We don't gauge fix, we don't quantize, but we first introduce the ghost. And then we like gauge fix and quantize. So in a way, we reverse the like this ordering indeed.
And just looking ahead, will the set of all these C fields in string theory, in string field theory, will that be the states of various different ghost numbers on the string?
Yes.
And the anti-fields will be like B0.
Yeah. So okay. So we will define. Okay. We will. Yeah. So they will also have the ghost number. I mean, but the worksheet field will have like. So all the so what we will do is, so string theory on the worksheet, you have I mean, okay, I will discuss tomorrow, but just
so that we are
Yeah.
oriented.
So,
Yeah.
so on the worksheet you have so you have this Hilbert space which has elements of all Ghosh numbers.
Yes.
So those elements we will divide. In fact, we will divide into field and anti.
And
So
is
it
that-
already has everything.
And are the anti-fields like things that have annihilated by B0 or does B0 play a
No. So a Ghosh number, B0 will play a role, but I mean, okay, we will see in
Okay.
precise manner how it will happen. Yes.
Sorry, but so let's say you have a C1 and a C3. These are gauge fields. One form gauge field and three form gauge field.
C1 and C3. No, these are Ghosh.
Okay, this one because H1 and H3.
H1 and S3, they will be in phi A.
So one form and three form.
Three form.
There's a three form symmetry which H3 goes to
Right.
H1 something.
Right.
Like one form H1 plus the other.
Right.
And the gauge parameter of three form also transforms under this one form symmetry. So how many goes up?
Whatever like number of this gauge invariants you have, I mean, so this chain will never. I mean, okay, it will depend on how many like level of your gauge transformations you have.
But is it two or three? Like is it?
So for three form field,
Is it one for three? One form gauge symmetry and one.
so for one form you will have just one.
It will be 3 plus 1, right?
Where for three form field,
3 form.
no, he's asking for
Yeah.
one form.
It will be whatever number you need for the three form gauge symmetry and whatever number you need for the one form gauge symmetry, or you have to treat the.
No. So I mean, what is your system? I mean,
You're talking about the Green-Schwarz mixing, right? The fact that the three-form field also transforms that.
Even the Green-Schwarz mechanics.
Yeah. I don't think you change that out.
I see. Then I'm confused about the grading of the letter.
okay. So okay, let's go ahead. So how do we introduce and what are the properties of these antifields? So what we do is we assign a Ghosh number and parity to our this field and antifield. So let's denote this Ghosh number by GH and the parity by epsilon. So Ghosh number of original phi I is 0 and Ghosh number of this C introduced at step S, we assign this Ghosh number S. Okay, and epsilon is epsilon of this ghost. The parity of this ghost will be related to parity of this your level S gauge transformation by the amount S. Okay, all this modulo 2.
So it keeps changing.
Keeps
What?
yes, yeah. And for anti-field, what we do is Ghosh number of anti-field should be such that it is opposite of the Ghosh. I mean, okay, so it differs from the Ghosh number of the field by this amount. So the sum of the Ghosh number of field and anti-field should be minus. Okay, and the parity of this anti-field should be opposite of the parity of the field. Okay? So this is the only criteria we impose on the this anti-field. So now next step is we want to write down an equation which will determine the gauge structure of the theory. So for this we will need now this notion of anti-bracket. Okay, so we had like hinted in the last discussion. So this is a more formal definition. So let's suppose x and y are two functions of fields and anti-fields. So we define the anti-bracket of x and y in this way. Okay. So xy bracket is del rx by del phi a, del ly by del phi star a, minus del rx by del phi star a, and del ly by del phi a. So the subscripts L and R means that the derivative acts from left and right. Okay. And you can also write this anti-bracket. Suppose you call your field and anti-field. So let's suppose your this index A runs from 1 to capital N. Then both, if you have both phi and phi a star, then this small index A will run from 1 to 2A. So if you collectively denote this field and anti-field by this ZA, then this anti-bracket can be written in this kind of simplicity. Okay, so this just a few one slide about this derivative. Because we are dealing with ghost field and fields with these alternate statistics, so you have to be careful with this how you are taking derivative and so on, whether from left and right. So suppose, for example, if your phi is a fermionic field, then if you take derivative from right, then it will just be A. But if you take derivative from left, then it will pick up a sign. So that's why I mean keeping track of sign is important. And it's a simple. I mean, if you just give some thought, you can relate the left and right derivative by this sign. So it's just some bookkeeping device. And this anti-bracket satisfies some, again, graded anti-symmetry property. Xy is related to yx, again, by some sign, okay? And they also satisfy this graded Jacobi identity.
Just as a triviality. You just
Just
work it out.
triviality, yes. And the Gauss number of this anti-bracket is 1, okay? So Gauss number of this bracket x, y is Gauss number of x plus Gauss number of y plus 1. And it's also easy to work out if you just follow the definition and the Gauss number of phi star. So basically, what you have to do, the derivative with respect to a particular field reduces that field. So basically, we assign the Gauss number with, Gauss number with a derivative, this minus, okay. So because it reduces that field, so it will reduce that Gauss number. So if you just keep track of this, then you can show that the Gauss number of this bracket is 1. And the parity of this anti-bracket is also 1. So parity of this anti-bracket is parity of x plus parity of y plus. So now suppose if B and F are some bosonic and fermionic functions of the field and anti-field, then you can show that if B is bosonic, then it takes this simple form. So the two terms just add up. And you get the factor of 2. But for fermionic, it vanishes. Okay. So now let's write down an equation.
And this was because the field and anti-field are opposite status.
Yes.
Opposite.
Yes. So now let's suppose S is an arbitrary bosonic functional of the n fields and anti-fields with Gauss number 0. So S we are considering to be a bosonic function, but it depends on the fields and anti-fields in some generic way. So Gauss number of S is 0 and its parity is 0. And if you treat S as an action, okay, the standard QFT-like action, then the classical equation of motion would be just given by del Rs by del phi A equal to 0 and del Rs by del phi star A equal to 0. Okay? This is a Euler-Lagrange kind of equation, but we are not going to analyze this equation. Okay, we will consider this so-called master equation, which will encode all the information about the gauge structure of the field. Okay. So the classical master action is defined by this equation. So you demand this anti-bracket of this quantity to be 0. Okay. So basically S comma S, which is this 2 times this del Rs by del phi A, del Ls by del phi star A, this is 0. So since we have doubled the number of fields in our system, it is not surprising that we can impose this condition. So this condition we are imposing on top of Euler-Lagrange equation. Okay. But since we have doubled the number of fields, we can impose
This is an after.
This is after.
So it's like the BD equation you introduced last lecture.
Yes.
So there's this plus dynamics.
Yes. But not all the solutions of this equation will be useful for us. And the physically interesting solution must satisfy certain conditions.
The analog of BRST.
Yes. So, okay, let's see what conditions.
Is A summed over?
Sorry? Yeah, A is summed over. You have to consider all the fields and pieces.
So understand you're just putting this by hand?
Yes, right now we are, we are putting by hand.
Okay. So why did you say that this is optional condition?
So right now we have not imposed okay, so this is the equation, this is the on-shell condition. But this equation we are imposing irrespective of whether you impose this condition or not.
I was thinking of that as like his equation from last time.
Yeah,
Which is just the statement that under these gauge transformations, the action is independent. So one of them is like 5 stars you think of as like a source for the gauge transformations.
Yes.
Now this is just a statement that if you change the action, replace a phi by its gauge transformation, the action.
But this is something classical. There was some.
Yeah, this is classical. This is everything is classical. In the last lecture, that was just a motivation. So how do we, people use the BRST formalism to come up with this kind of equation, and this kind of equation in the BRST formalism precisely encoded that transformation. Information about that transformation. Right now we are just imposing by hand. So let's see what are certain conditions which we demand from this. So to find these conditions, let's first analyze what are the gauge redundancies of this classical master action. Okay. So we will call this S as classical master action.
Is it appropriate to think of this as roughly that the S is like the Legendre transform with respect to fields?
Right.
Introduce a source for both fields as well as gauge transformations. And Legendre transform with respect to the source for fields, but not.
Yes. Right. So, since this classical master action satisfies this classical master equation is comma is empty bracket equal to 0. So let's take the this derivative with of like this condition. Okay, del R by del ZB SS equal to 0. So if you like work it out, then you can show that it takes this form del RS by del ZA RAB equal to 0. So del RS by del ZA is like analog of S0A, S0 comma I, the equation of motion, and RAB is given by this this quantity. Okay, so which means that the classical master action is invariant under this term because this is basically of the form of Noether identity. Okay, and for this RAB, so so the classical master action will be invariant under this transformation. If you make ZA to ZA plus RAB ZB, where this curly RAB is given by this object, then for this RAB you have this Noether identity. So it's a redundancy of this generalized like this classical master action.
Sorry, I was basically just say what you said.
So basically this okay. So from like this equation, we find that it satisfies this equation.
Z was
Z is the like both field and entity. It's a like collective everything.
okay.
So you have this equation of motion del RS by del ZA times this RAB, but and this quantity is equal to 0. But this is precisely this Noether identity. I mean, we have written now. It's an equation of motion times some quantity equal to 0.
How did you get RAB from?
Oh, you just take derivative. I mean, of this master equation, and I mean. So you have this. This is your this. You just take derivative of it.
Where was RAB in this?
Oh, RAB is like this combination which will. So when you take the derivative, so you will get
del S by del phi star RAB.
no. So RAB is this quantity. I mean this. Okay. So there's some algebra involved. So when you take the derivative, there will be a term with a single derivative, and then there will be a term with two derivatives. And then, okay, you have to like rearrange things, and you can put it in this.
The structure. This R was one.
No. This RAB is just
defined.
it's just defined by this. It's
Okay.
not like something previously.
Okay.
Is this symplectic?
Yeah, that is symplectic form. So if you take the derivative, you can show that you can put it in this. So which means since it satisfies this classical master equation for this particular this value of RAB, then it means that the classical master action has this gauge redundancy. And now, if you take this definition of RAB and take
Sorry, what was the gauge redundancy? So that
this is the gauge redundancy for this expression of R.
so Z equals to Z plus this because
It satisfies the Noether.
because if you put del S by sorry just
Yeah.
Sorry, I'll be stupid. So that was you're saying you take that and you get this
Yes.
and
RAB is just defined by like this one.
this
Huh.
and so and what did you say now?
So I'm saying since it's this for this RAB, we have this Noether identity.
Yeah.
So if you make this transformation, I mean it's like a redundancy. I mean your classical master action will remain valid because it satisfies the this Noether identity.
Or solutions to the master equation that I'm updating.
Solution will have also have yes, but okay. I mean solution we have still not talked, but yeah.
Is this the trivial case transformation?
No. I mean this is some. I mean these are generic. I mean it's they satisfy some. I mean they will have trivial part. They will have like non-trivial part. So if you have this RAB now, so to find the conditions which we want to impose on the equation of motion, you just take again this derivative of this Noether identity, and if you put on-shell condition, which means you impose equation of motion, then if you're working on-shell, then you can show that this RAB satisfies this condition, which means it's basically a nilpotent matrix. And
What is the on-shell condition? The equation that
Euler Lagrange equation equal to 0. Okay. So since this RAB is a nilpotent matrix, then from linear algebra, we know that the rank of these nilpotent matrices should be are less than half of the total dimension, less than or equal to. Okay, so rank of this RAB must be less than equal to n. And the physically interesting solution of these classical master equations are those for which this rank of RAB is exactly equal to n. Okay, so physically what it means is that the classical master action S exactly has n like gauge redundancy which are enough to throw away these antifields phi star. Okay, so why we want to throw away phi star? I mean, so okay, I'm going ahead. So for quantization and so on, this phi star we have just introduced for like encoding the like gauge structure of the theory. Okay, but for quantization, what you need is you need the field phi I and then the ghost for ghost and so on. Those are needed for quantization, but the role of this antifield was to encode the gauge structure. So when you want to quantize the theory, you would like to gauge fix these fields phi star A. And the interesting solution of this classical master equation are precisely those which can get rid of this phi star. Yes.
Yeah, I missed something. When you say function, the action is now a function of all the. So how do you
Fields and antifields.
that action from the.
Yeah, so we will discuss. I mean, okay, construction is like okay, we will see. I mean, how you like there is a how far you can like construct. So we will come to that.
Given the original action,
Yes,
let's
ma'am.
say yang is fixed,
Yes.
we can.
Yeah, so there is a procedure. There is a procedure you can. There is a procedure.
So setting this phi star equals to 0 is equivalent to gauge.
So if you naively set phi star equal to 0, then you will get the like original action. Okay. So okay, so there is this condition basically. What so along with this condition that its rank should be n, we also impose this boundary condition on the classical master action. So what we demand is that if you set anti-field to 0, then it should reduce to your original action S naught phi without any ghost. Okay, the S naught which you like, which I mean the starting at S naught without any ghost. So this is one boundary.
That would be natural if you thought of phi star as sources for each other.
Yes, right. So and it turns out that these two conditions, that if you impose this boundary condition and then you demand the rank to be n, then these two conditions are enough to guarantee that the solution of classical master equation exists and is unique up to some canonical transformation. And these canonical transformations are those which preserve this anti-bracket system. So up to this
Solution to the classical master
Equation.
equations. What is so that solution means by specifying
so solution of this equation.
so you're saying in terms of what the action is
Yes.
at phi star equals 0,
Yes.
we can construct it as a function of x.
Yes.
So that's what
Yes.
Omkar was asking. Like given the classical action with no phi star, how do you construct it?
Construct. So you have to like.
Also setting phi star equal to 0 should even remove the ghosts.
Yes. Yes.
The ghost, not just
Yes.
any ghost, but also.
Yes,
Yeah.
yes, exactly. So that's why I mean it's a like a not you cannot construct really, but at least there is one guideline. You yes. So
Oh no, but sorry. Now I understand what he's saying. Saying we said phi star equals 0, but you still have the ghost.
no. So ghosts are also
That-
bound.
that's a
So we
boundary
demand.
condition.
So this is the boundary condition we are in. The ghost should also vanish. I mean the ghost term should also.
At phi star equals 0, there are no ghosts.
There are no ghost terms. So it is the.
Oh, it's like B with B multiplied C.
BC.
So
B0 then goes to
yes.
B.
So okay. So just to give some intuition, so this above boundary condition for the classical master action. So this implies, as Siraj was saying, you can expand in a power series in antifield. Okay. So let's suppose you have first stage reducible theory. Then okay, so you can expand in this way. So you have S naught, and then you have some phi star A. So in terms of antifield, you have then this TA. TA is some quantity which you want to construct. Then you have phi star A, phi star B, then some quantity TAB plus dot. Okay. So this expansion you can write down, okay, for this classical master action. And so for if your first stage reducible theory, then okay, I mean it takes so S naught phi. Then you have this phi I star, and then you have some C star, which is this antifield. Then this eta A star denotes the this ghost variable, anti-ghost variable with the like second level or this gauge transformation and so on. Then you have this quadratic pieces, so phi star, then C star, phi star, and then you have a cubic level phi star, and so on. So this is the general structure you can write down, and then you write down all possible like way in which. So okay, so another like condition you demand is since S has Ghosh number 0, so all term in this expansion should have Ghosh number 0. Okay, so since antifield have some Ghosh number, and then this ghost has certain Ghosh number, so you basically combine them in such a way that okay, you have total Ghosh number 0, and all these like 10. So here I mean you have okay, you have T alpha beta gamma Z alpha A, and then the A B and F A alpha beta gamma. So these are just some constant for now. These are just some constant which appear when you try to write down this action.
So when you set the anti goes to 0, the resulting object can only be made of the bosonic field, right? Because
Sorry?
And when you set the anti-fields to 0, the resulting object can only be made of the boson.
Can only be made of this phi A.
Small time.
Yeah, small phi. It can have bosonic formula. I mean, okay.
Yes.
It depends on. Yes. So so you have like so for example, this phi I star C alpha will have Ghosh number 0, and to soak up the indices, you introduce this quantity R I alpha and so on. And then similarly, you have C star alpha. Then okay, you can have this eta A, and then to soak up these indices, you have this quantity Z alpha A and so on. So right now, all these constants are just some constant, but what they will turn out to encode all the gauge information about the theory. They will turn out to have all these structure function we introduced, this F, this A, B, I mean M, T, E, and so on. Okay.
So you just introduce all the series and so on.
Yes, and so on. Yes, right. Yes.
And you get some differential equations.
So now, so yes, so now what you do is you put this expansion in the classical master action, and
You also have ghosts for fields and antifields both.
no, not. So we had ghost associated with all the gauge transformation, and then associated with fields and ghost we had anti.
Oh, sorry, can you go back here, please?
Yes. So we had, so what is our system? So let's see, I mean, for this first stage reducible theory, we have these small files. Okay. Then associated with 0th level gauge transformation, you have this RI alpha. Okay. So you will have some gauge parameter lambda alpha. And then associated with first level of gauge transformation, you will have another some lambda alpha too. Okay, so you have two level of like gauge transformation. So associated with 0th level, you introduce this ghost field C alpha. Associated with the first level of gauge transformation, you introduce this ghost field eta A. Okay, and then associated with these three kind of field phi, C, and eta, you introduce these antifields phi star, then C star, and then eta star.
Okay, so C are the ghosts for
Ghost. C is the host, and eta is host for host.
Level 1, stable.
Yes.
So on this section, what's the difference between del and del R?
There was a relation between del L and del R, so you can like relate. I mean, it's just that I mean, you can work with any of the derivative, but then you have to keep track of some. But in this master action, it's written in a way so that I mean, okay, both del R and del L copy.
By computing the Euler-Lagrange equation from this section.
Yes. So for Euler-Lagrange equation, I mean, in fact, you can like work with any of the.
They just differ by sign.
Yeah, they just differ by sign. But, I mean, it does not really matter, but you have to keep track of sign when you are computing like derivatives. You have to keep track of all the like sign.
Differ only by saying because this is Bohr.
So no, for anything, like it, they only differ by what you have to cross, right?
Right.
And taking the derivative.
So, so now what you do is you put this expansion of this classical master action into your classical master equation, which is empty bracket of S comma S equal to 0. And so in the classical master equation, now that also can be expanded in terms of this ghost and antifields. Okay, and the coefficient of each ghost and antifield should now separately be 0, because you cannot combine terms with different ghost numbers. Okay, so you demand that each like term with a particular ghost number or antifield power should vanish. Okay,
Ghost number is an integer value,
integer value.
not set to.
No. So and these coefficient which which appear in this expansion of this anti bracket being 0. So these coefficients precisely dictate all the relation between the gauge structure of the theory, and in particular all the commutator which we had like seen earlier in studying this gauge theory, they are obtained by setting these coefficients to 0. And so this shows that this classical master equation is a compact way of expressing all the information about the gauge structure of the theory. So this was the main motivation for introducing this classical master equation and classical master action. And now we also have this BRST symmetry of the classical theory. So in this formalism, this BRST symmetry is present even before the gauge fixing. Okay, so if you have, and this is generated by this anti-bracket. So if you have a BRST transformation of let's suppose you have some functional x, which is a function of field and anti-field. Then if you make this transformation, delta of x is given by this anti-bracket of x comma s, then you can show that action will remain invariant because it precisely satisfies this classical master equation. And it's also easy to check using the property of this anti-bracket that if you act twice, then this operation is nilpotent. Okay, so delta v square is 0. And in fact, if you work it out for closed irreducible theory, precisely these anti-brackets, then you can show that they are precisely given by the this BRST transformation, which we know for Young-Mills theory. So delta v phi, in the last lecture, we had written down this transformation, and they precisely turn out to be like these. Okay, and these are the usual BRST transformation parts. So this shows that the BRST invariance is inbuilt in the BB formalism from the beginning. So we have not done any quantization. We have not even talked about any quantization or even gauge fixing so far. It's present even at the classical level.
It's or at the higher level.
Higher level you can have this. Yeah, I mean there can be more terms in general. I mean but for closed irreducible theory, these will be there.
So in the usual BRST, we also have this Lagrange multiplier.
Yeah,
and so on. That's not right.
It's okay. Yeah, I mean I've only written for pi and ghost. Lagrange multiplier, okay, you can get rid of. Last lecture, I mean it was not necessary to write,
But it was Lagrange multiplying a gauge fixing condition.
right.
So that since that's not there, it's somehow just not there. Right?
Just not there. Yes. Yeah. Yeah, it will not be there in this case. Okay, so let's consider next the quantization. Okay, so for quantization, first we need to gauge fix the theory. Okay, and since BB master action is a function of both field and anti-field, we have enough number of these gauge invariants to fix half of them to whatever value we like. And the space which is fixed by this gauge fixing condition has a technical term. It's called Lagrangian submanifold. Okay, and we will usually choose gauge fixing condition which eliminates all the anti-fields. But this, if you naively set phi a star equal to 0, and it's then it is not a very good choice, okay? Because it will give back this original action as not phi, which has the issue of gauging. So a standard way to eliminate this anti-field is by what people typically do is that you set the value of anti-field to be this. So you introduce a functional psi, which is a function only of fields, okay, not anti-fields.
That's a gauge fixing.
It's a gauge fixing condition, and this parity of psi has Grassmann odd parity, and Gauss number of psi is minus. Okay? And so this phi star a can be expressed completely in terms of this phi a. So apart from these conditions, this gauge fixing fermion psi is arbitrary.
This psi is a function of fields as well as anti.
No. This psi only fields. Only fields.
Then how do we have Gauss number minus?
Yeah, it can have.
I thought the ordinary field, let's say we will do Young-Mills theory, the ordinary fields will have Gauss number 0, right?
Ordinary field will have Gauss number 0, but then you have Gauss
when you say fields, you mean including
Gauss. Yes. Yes. Okay. So it may appear that fields and anti-fields are on a completely different footing. But as we mentioned earlier also, we can make a field redefinition which can mix field and anti-fields, provided the anti-bracket is preserved. So for example, if you make this redefinition, phi a star goes to some phi tilde a star.
So is that basically the gauge fixing condition with the role of the gauge transformation parameter being played by Gauss?
Yes. You met this redefinition. So phi tilde A is given by phi A, and phi tilde A star is given by phi star A minus del psi by del phi A. So then you can show that the anti-bracket will be preserved. So in the original system, phi A, phi star B anti-bracket would be simply delta AB. And in the new system also, phi tilde A, phi tilde star B is also delta AB. So this is an allowed like transformation.
Like a symplectic.
Symplectic transformation, yes. And then we can think of this gauge fixing condition as setting the new antifield phi tilde star A to 0.
But in such a way that there's no infinite family of transformations.
Sorry?
But in such a way that there's no infinite family of gauge
Everything is gauge.
Yeah, gauge fixed. Okay, so after this gauge fixing, we can now quantize the theory. So
And that function was only, sorry, and so that function just was a function of both original fields as well as costs.
yes.
And will it, in the case of Yang-Mills theory again, just would it be like, say I wanted to connect with del dot A equals 0. So then it would be the gauge transformation of that condition with the gauge transformation parameter replaced by cost.
Yes.
But for the more complicated guys, we will need to fix also the gauge transformation for gauge transformation.
Yeah, exactly.
Nice.
It would be completely arbitrary. It would
Which one?
depend on.
Yeah, I mean, so it is arbitrary in the sense, I mean, you have to fix, I mean, take some value. But in the cases, you know, you would like to, I mean, you can choose any like gauge.
It's the same exercise picking a good gauge or a
Yes.
But also for the gauge
For the
yeah.
gauge for gauge also. So with this gauge fixing, we can now quantize the theory. Okay. So suppose you write down a path integral expression for some correlation function of some object x, which is a function of some field anti-fields. So this delta is the gauge fixing like delta function, and then you have this e to the power I by h bar w. Okay. So W is a quantum generalization of the classical master action S. We will shortly see what is the connection between this W and S. We are allowing for more general.
So here your correlator depends on the sign.
Correlator,
that you
yeah, because it's a gauge fixing condition. I mean, this is what you also do in pathing, in normal path, right? You introduce okay.
And that X is a determinant.
No. This X is some functional of anything. I mean, suppose you want a correlator of X. So I mean, it could be phi. We could also set. I mean, we are going to set X equal to 1 to derive the.
No, but in normal Kadipova, once you introduce a delta function, you also need a determinant.
Yes. Yeah. I mean, okay. So I mean, okay, there will be a determinant. I'm very schematically I'm writing.
But so why does the correlator depend on your the gauge fixing condition that you?
It will depend. I mean, it will depend in the sense. I mean, you can show that it will be independent of psi. If you like work it out correlator, it will not matter. I mean, what is your gauge fixing formula? In fact, we are going to find out precisely the condition for which this correlator will be independent of psi. Yeah. So for this path integral to make sense, we must ensure that it is independent of this gauge fixing condition. Okay, as you are asking. So this gauge fixing, since it is done by functional psi. So suppose you deform psi by an infinitesimal amount delta psi, then the change in the path integral would be given by this. So I of psi minus del I of psi plus delta psi minus I psi. So I'm setting x equal to 1. Okay, so just normal like partition function. Let's work it out. So this will be the difference. Okay, and now I mean if you like do this, since this delta pi star is infinitesimal, you just do an expansion. You can show that this reduces to this up to order delta psi, and you ignore all the terms of order psi, delta psi square, and so on. Then it reduces to this, where this operator delta has this form -1 to the power epsilon a plus 1 del r by del phi a del r by del phi star a. Okay? And for this path integral to be gauge independent, this variation must vanish. Okay.
We go through that slowly. This is like the equal to the independence of under BRST.
Yes.
I mean, changing gauge transformations. There, that was BRST sort of exact transform. Right? So please say that this again. So how do
we get this?
Yeah.
Yeah. So basically, we just do a Taylor expansion, and then we just combine. I mean, you can show. Okay, just some few line of algebra involved. So you just do Taylor expansion, subtract the like leading pieces, and then what remains is this operator.
Why the result?
Oh, because I mean, we don't want this to be gauge independent. So whether you use psi or psi prime, I mean, it should be the
Why we
same.
want it to be, why is it zero?
Sorry, why we want it to be?
No, why we want it to be zero is because it needs to be
Yes.
independent of type, but
Yeah.
why is it zero?
Why it is zero? I mean, we are demanding that because we want it to be zero, so we just set it to zero.
W so that it.
Sorry. Yeah. So W. I mean, W is zero. I mean, so okay. So this is the condition you get. And for this quantity to be like gauge independent, then this quantity must vanish. We are still not satisfied in what is W, but now we are going to find.
The W will be given in terms of our S, but
yes.
with some modification
Some
in order to make sure this is.
Yes, it's true. For the gauge invariance of this path integral will be ensured by demanding that this delta, which was an operator which acts on this e to the power I by h bar w, it vanishes. And if you like act with derivative, then you can show that it takes this form half of w comma w equal to I h bar delta w. So w comma w is the empty bracket of w which we had introduced, and delta is this operator. So this is known as the quantum master equation. Okay, and w is known as the quantum master action. So we have now three action in the system. So we had original action S0, then we introduced this classical master action, and now we are introducing a quantum master action.
Classical master action is with phi and phi star.
Phi star, and yes, all the hosts.
And S tilde will be related to S0.
Yes. So I'm just going to say, so this quantum master action W can be expanded in power of h bar. Okay. So W you can write some S tilde plus h bar to the power n. Let's see what is S tilde. So if you insert this expansion in this quantum master equation, then you can show that S tilde must satisfy if you set order h bar to the power 0 term to 0. So each term in proportional to some particular power of h bar must be 0. So at order h bar to the power 0, you can show that S tilde satisfies this classical master equation, which means that S tilde is the classical master equation. So this shows that when we quantize the theory, we need to add new terms to the classical action to make the path integration consistent. And so this is like adding counter term to the action to make your theory like consistent. So to ensure that you have this invariance, BRST invariance at the quantum level also.
Will these additions be local?
I mean, so for the theories, usual theories, they will be local.
They will be local. So I suppose what I was really asking was.
But if you have quantum, I mean, string theory, then okay. I mean, there could be.
No, but if we have usual theories with massless fields and so on,
Yeah.
it will be local.
Yeah. So they will be like the standard counter term we add in, like say normally normalizing the like theory. Say you have you.
So these are the normalization.
Yes. In fact, you can. So yes. So basically, I mean, okay. This is the point I'm going to make. Okay. So first, this operator delta is a singular operator. In fact, it's you have these two derivatives. So because these indices A include not only discrete indices but also some space-time index X. So the first derivative will give you some delta function, delta of x minus phi, and the second derivative acting on delta function will give you divergence. So in general, this will be like this is a singular operator and it needs a regularization. So due to this reason, unlike classical master equation, one is not guaranteed to get a solution of quantum master equation. And if you can regularize this operator delta, then it signals. So suppose you cannot regularize this delta, then it signals that you have anomaly in your quantum theory. Okay, so your procedure of quantization does not respect your symmetry. So in other words, if a solution of the quantum master equation exists, it implies that the gauge symmetry survived the process of quantization.
Can you repeat once again why delta is singular operator?
So here you have, so delta is this operator. So this index A includes discrete indices as well as space-time indices. So the first derivative will in general give you some delta function, some delta d of some space-time point x minus y. And then when second derivative acts on those delta function, it can give you divergence in general.
You get like delta function square.
Yeah, right.
Can you remember it's the shine?
Which side?
Is delta shine?
Here?
No. It's not in that slide. You're running the delta function.
function of phi.
Yeah.
This is just the yeah. So you have to set phi star equal to del psi by delta phi. So it's like you are changing this gauge fixing fermion psi by infinitesimal amount. So that is psi plus delta psi.
And can you explain why, what do you mean by when you are not able to regularize your delta?
So in general, suppose your theory is non-renormalizable. Uh, so, so there may be exist situations where you are not able to like renormalize your theory, regularize your theory. So in those cases, you will not have you will not be able to find solution of like this quantum monster equation.
As in you have an operator, right? This delta.
Yes.
What's the meaning of this? If you are not able to regularize this operator, what is the meaning of this?
So you will not be able to find some like some regularization scheme for which you have a finite solution of this equation.
Okay.
So you have to find some regularization scheme. You have to work with some regularized operator so that the solution of this equation. So that's all.
If I take a parallel gauge theory, the gauge anomaly will come out of this.
So in fact, no. So this. So okay. So what happens is, in fact, this is related to this point I'm making on this slide. This issue is related to the renormalization of the theory. So if the theory is renormalizable, then this counter term Mn, which are present in this quantum master action, they can be chosen to be the same as the usual counter term we had in the gauge theory. Okay. And BV, what it does is it already includes information about all these quantum terms because we are dealing with all the like quantum corrected like theory in one shot. So it knows about this solution of this quantum master equation, knows about all this counter term, etc., which should be present in the theory.
And
But suppose
they'll all be low.
they will all be low. But suppose your theory is like non-renormalizable. You cannot find a scheme whereby choosing a finite number of counter term, you can make the theory renormalizable. Then it's not that BV will give you a solution. It's just that if your theory is well behaved, nice, then it will already know all the information about the theory. I mean, at the quantum level. But if it is not renormalizable, then of course it cannot help you.
I was asking because in the previous slide you wrote that if you can't renormalize delta, it's not.
Yes.
So I will say
It's because if you cannot find any like this scheme where you can regularize this operator, which means the solution of this quantum master equation does not exist, which means like there is no regularization scheme which will preserve your symmetry at the quantum level, basically. So that's why I mean, so that already is present in this quantum master equation.
And it's looking ahead in string field theory, will there be a difference between S and
Yes, SW, S not everything.
even though there are no naive UV there?
Yes.
But
It's still, but there will be correction coming from this higher order voltages. So I will describe what is S naught in string theory, then what is this W and what is S. All three action I will describe in string theory. Okay, so maybe this is what I wanted to say about the BB formalism, and then next thing is we want to consider the string field theory. Maybe it's a good time to stop today.
yeah.
Yeah.
Maybe I should have asked at the time. You had these trivial, non-trivial gauge transformations and trivial. There's some way of thinking about that in terms of in some differential geometry language. And this just maybe let me say one more line about that. I mean, you have a generic function of phi. You might think that the surface of constant action. At least in finite dimension, that would be like a 4-dimensional. And then any vector that points along the surface will trivially lead the action in bed. But when you have some degenerate functions, then you like those are the kinds of functions that are needed. I don't see it's.
I think there, I mean, I think there are some papers in the like geometric for geometric way of looking at this BB and all the case theory. So I think there is a geometric way, but I'm not like yeah.
I was
Yeah,
roughly wondering whether this ES is like a normal one form on the surface and you're trying to construct a projector. I was wondering, maybe that.
By degenerate you mean zero vector.
No, I'm just like,
On the-
consider the function x squared plus y squared plus z squared. You set that equal to constant, you get a four-dimensional constant. But you take this function a, and that function is constant. You can, if you try to integrate e to the minus x squared plus y squared plus z squared, that makes sense. Because the degenerate surface is compact. Whereas e to the minus x will go on these other. So I was wondering whether
I think there is a geometric way of looking at it. but,
maybe it would, maybe I'll understand this formalism a little better if I just try to understand it at the level of integrating functions. So integrating functions. Geometrically.
You're saying the trivial ones, or the whatever you call it, the thing.
Yeah.
Just move it along. sir.
Right.
Yeah, exactly.
tangent direction.
Hmm.
So is there no analog of this BRC charge?
Of course, there will be. One can, of course, construct some observable sense.
But just following up on that, you told us about path integral, but now we also need a rule for what you can compute in this path.
Yeah.
Like the usual rule is that only the RST closed.
Right.
So what is the analog of that?
Yeah. I mean, so there will be actually. I removed those. Yeah, there is a certain condition. Yeah, there is certain. Yes. Yeah.
That are physical operators.
Yes. Yeah.
There will be an nilpotent operator. You can write down this nilpotent operator in terms of this field and anti-derivatives of the
Right.
anti.
And is it very roughly that if I had changed the action
Mhm.
in a way that obeyed the BB,
Mhm.
but I changed it with some epsilons,
Okay.
and then I differentiate with respect to those.
Mhm.
Those are the allowed operators.
Mhm. So there, but there will be some condition. I mean, it has to.
But I'm wondering if you can get that condition out of this. That you see, because
Yes.
any action,
Yes.
basically when we have operators, it's like an allowed path integral and you differentiate.
Right.
So you look at the space of allowed things, differentiate with respect to that, and then you inherit your condition.
Yes. Yes.
For orientation, I want to know what all these quantities are in standard SU and Yang.
You. So for UN, for UN Yang-Mills theory, it's the irreducible theory. So you don't have the ghost for ghost. So you just have simple ghost and so the quantum master equation will have all the like quantum corrected like quantities. So
But B will be your 5-star.
which we
B, the normal B goes
B goes
Oh,
to
B
5-star.
normal B will be related to some NP ghost.
will be 5-star, right?
Yeah. Yes.
So it's like B times C, you always get that combination.
Yeah.
So that's like so.
And all the higher levels are have zero coefficient.
Yeah.
And also then what is the gauge fixing? Psi of pi.
Yeah, we will. I mean, okay. Jay, I mean, okay. There is a. We will discuss. I mean, what.
Okay, but that will not be anything like Lorentz gauge or nothing.
It's up to you.
It's up to you. I mean, so.
No, because that would not come out with about some post number minus one for the.
Right. But usually, what you will do is okay. You have some. We will introduce some string field, and then we will put some like gauge fixing like a condition which is called Siegel gauge. So B naught plus I equal to G. Okay, so that will be like.
Yeah, so that is in the string field. So
Yeah.
I was thinking in a much simpler, like the standard Yang-Mills, would I be able to introduce Lorentz gauge in this?
Yeah, you can work with Lorentz gauge.
You're saying the lambda L dot A. Where is that? Where is that?
come out?
Where is
Yeah,
that? There's
so-
no that you can get, but where is that? Lambda.
Yeah, so I think you have to have, there is some way, I mean, so the psi you have to choose appropriately, which will input some way, I mean,
That can be chosen to fix Lorentz input.
which can be chosen this.
No, but it's a good question, right? Because for instance, if we do lambda del dot A and then we do lambda square, we get a del dot A square,
Yeah.
but that has no ghost anything.
Yeah, right.
And that doesn't seem to come out of your side.
It will be, I mean, so ultimately it will boil down to like,
Your side will be like the determinant. Because a small
so
transformation.
this psi will also have this, okay, vector field. I mean, you can choose, okay.
But then we have host number one.
Yeah, host number
Minus
-1, so it will be multiplied with like some host. And as you were saying, I mean, here, I mean, at this level, we are representing this Gauss transformation by like some host.
Yeah. But that. So I was also thinking that, but as Omkar said, what there when we do it, it's the variation of the gauge fixing condition. But we also have an explicit gauge fixing condition.
You're right. So so if you precisely parallel what
condition will appear as a anti-field.
yeah, no. So
But where is del dot A the whole thing square?
no, so I mean, what is it?
Host number 0. Where is 0?
So what I think you can recover is I think right now I don't recall all the details, but you can recover the results of gauge fixing in this Lorentz gauge by this formula. There is a precise like derivation of this. Now I'm not recalling all the like details, but
It will be interesting just to see where the del dot, what the role, how that comes out.
yes, yeah.
Because how it fixes the propagator. I think it's a good goal.
So del dot A square can be made linear by introducing this
Lambda.
auxiliary
But
lambda.
that's also host number 0.
That's also host number.
So where is the host? How by introducing host number -1 we get? You can get the variation, the determinant, right? But what about conditions? Right? It's very-
Lambda will appear in the BRST transformation.
But you know,
The lambda is the anti.
okay, so that's host number 0. I thought
What do you want
do you
to?
have a host? Do you have an antifield?
Host number 0.
Yeah.
Yeah.
Which host number 0?
Yes.
No, not antifield with ghost number 0. So associated with the ghost number,
Ordinary gauge field, there's a
there will be a
Ghost
field
number
with
0.
-1.
That's it.
That's
No. Is there an antifield with host number 0?
So let us see. It there will be like antifield with all possible ghost numbers. So let us see. So this was your like condition. So for example, if you have like ghost field is 0 for ordinary 5, then the antifield will have ghost number -1. But then it's not like. But I think so. But what exactly you want to see? Like, I mean, in what step you want to see del mu A?
Yeah, you want to see where the. I think what Omkar is asking, and now that's my question also. Now that he's asked it, is that you have to introduce something in terms of the original fields. Forget all posts. Then make that propagator value.
Yeah.
So you need some purely.
So you can get this propagator.
No, but where in your formalism?
Yeah. Okay. So
is that introduced?
yeah. So okay, we have to like write it down for like this particular theory. This.
Yeah, but the confusion is that you seem to be introducing only things with question.
Yeah. So what you do is okay, you follow this. I mean, okay, you work with this, and then you have to choose appropriately psi, and then okay, it will come out. I mean, okay, that I can guarantee. But okay.
Where is the ghost number 0 thing? That is
all terms are ghost number 0, but
without any C's.
Oh, that okay. That is just in S0. Fine. Yeah.
But then how is your propagator made final?
Yeah, so propagator will involve like okay, some maybe I can look it up in more detail. Right now because I don't recall.
Yeah, your gauge fixing lambda times b.
Yeah.
Yes. Yeah. So yes, you have to like I think what. Yes. So that was the BRST transformation.
I thought as the solution including about the BRST charge in the BRST problem.
Right.
Generates.
Transformation.
although in the usual way it would have been the usual community format is 90.
Right.
And in string theory, this extra this connection between this quantum effective action and classical action, will that be like this part of moduli space that generates contact?
What do you mean size?
Meaning if you do something like plumbing fixture construction,
Right.
you associate part of it as propagators and part with vertices.
Yeah.
I see.
And the vertices will get fixed.
Just a quick question. Like I always get confused in this. When you are talking about the physical equivalent, physically solutions, you always talk about a particular ghost number, right?
Physical
Like the
string theory.
yeah, a
Ghost
particular
number 2.
yeah, whatever fixed ghost number. What is the reason for that?
I will discuss in detail tomorrow.
Okay,
Yeah. But yes, I mean, so the ghost number 2 is where all your like physical
yeah. What is the
space-time field.
statement? Why do we look at that ghost? It's specific ghost number.
So that you see, I mean, which like at what ghost number fields enter in your S matrices and so on. So that and also like which give you the physical sketching matrices. But maybe there is more mathematical like answer also.
But is there a physical answer? Why do we look at the specific ghost sector?
So this is what I'm saying. So that ghost number 2 sector is what enters in the S matrix. When you compute S matrix.
Ghost number 1, I think, gives you 0.
Ghost number 0 will give you 0. Or it will be some trivial. It will be some trivial.
That's not easy. So maybe it's BRST.
Yeah, I'm going with that. So, yes.
BRST.